Welcome to an Optimus Solutions technical webinar on load study. Today, we have a full crew. My name is Tom Zhang, a senior engineer. I have Cephas, who's our mechanical engineer, and Sarah, our key account specialist. Hey guys.
Hello.
Okay, so today we're going to talk about load studies. Why it's important, when's a good time to use it, what are some of the details on just what it is. So to start, what is it and why? And I'm sure you guys will have certain questions throughout. So a load study is an analysis that determines the weight on the tire, shell, rollers, etc., whatever it is, and if it exceeds the industry standard or not. And a lot of the rotary kilns, rotary dryers are designed for a certain amount of weight or a certain amount of load. If it exceeds it, that's where you have issues. One of the things that Optimus has started doing, this is for your 3 piers or more kilns, is we are now able to consider misalignment effects. Overall, in terms of the misalignment, anytime you move that to the left or to the right or up or down, that will create an additional load. So one of the questions will be, why a load study? Why do these things? Again, OEMs will typically design the kilns, the dryers, very close to the limit. If that limit is, say 10,000 psi on the tire bending stress, they'll design it at 9,500 or right at. When changes happen, because most units are designed relatively close to the limit, when changes happen or anything that upsets the weight, you have a very real likelihood of either just direct failure or accelerated wear. I mean, we've considered so many different things, chain, refractory, shell thickness, any changes in your tire and roller geometry. If you got dryers on the flighting, if you want to change from, say, a 1/4 inch flighting to 1/2 inch flighting, you effectively double the weight on your flighting. That matters. Got customers that increase their production rate, say 30%. That matters. Hey, what if we slow down the unit? Does that matter, right? Or anything related to just changing weight. Cephas, I mean, you've done some of these now on it. What's your take on some of the changes that you've seen?
For most of the studies that we have done, the changes are due to customers or clients wanting to increase production. Now, with the increase in production, it means you're going to have the load also increasing. Now, as you mentioned earlier, most of the designs are close to the limit of the materials. So if you increase production, then there's a good possibility that the stresses or the metrics that are used to measure some of these limits might be exceeded. So that warrants a load study to ensure that they are still within limits, or if they are outside the limits, then we propose solutions that can be used to mitigate those effects.
Right.
So what kind of metrics are you looking at if somebody were to say they want to increase production a certain day? What metrics do you look at to make sure they're not exceeding limits?
So with production,
go ahead, Steve.
Okay, with production increase, the main issue here is the weight or the load on the load bearing system. So we are talking about the stresses in the shells itself, the Hertz pressure on the tire and the roller, and also the bending stress on the tire itself. So these are the three areas that we'll be looking in terms of stresses. Then we'll also consider the ovality of the tire to see if it's also been affected. So these have standard limits that we try to work within.
Right. And these limits, what's cool is we're going to actually show some of the results of these limits. But yeah, overall, they're pretty standard industry limits. The thing we're actually working on is why these limits, why it matters, and where did it come from. So this is kind of the next phase into our next generation of load studies. Let me see here. There we go. Our Optimus process. Okay, so Sarah's very familiar with this part in terms of what we do just about every day. I call it Optimus process because we do it all the time, and it is our not our methodology, but just our day-to-day communication, how we help the customer. And this is kind of taking it from the very, very beginning to the very, very end. Normally, the customer has a problem. They either call Sarah, they call someone else in one of our other sister companies like Industrial Kiln, and if it's a complicated problem, Sarah gets a call, and then I'll let Sarah kind of go through this part.
So anytime a customer calls and has an issue like this, or a lot of times, in working with Industrial Kiln and Dryer, we encounter problems like this where it gets passed along to us, and what we'll do is try and schedule a conference call with you as a customer and try and understand what the problem is. And a lot of times we find that you're dealing with symptoms of the problem, and our goal is to get to what is the actual root cause of that problem.
Right.
And a lot of that is fact finding, asking questions.
Right. And once we figure out what the problem is, we then go, okay, so what can we do to help you solve the problem? Once we get agreement that whatever our service is, whatever we do to help the customer is agreed upon, then the next thing is always, okay, what's our metric of success? What's the expectations we're going to set for that service? So like, for example, with the load study, hey, you know what, 10,000 PSI tire bending stress is what the metric should be. Hey, you know what, we are very conservative, so let's go with 9,000. So that's a discussion point that we can have with each of our clients. And then once we get that agreement, once we get everything, all the expectations set, we perform the analysis. When we perform the analysis, what's cool is we always do an internal review first. And then if my intuition is telling me that there's not enough review, or there's not enough depth that really makes sure that we get what we need, then we go external. We ask the plethora of different technical gurus at certain either processes in the industry or equipment like baghouses or fans or fractor, whatever it is. We reach out to those people, and then we get a good feel for an analytical view, so something that we calculate internally, and then something that we get with experience. Then we get the report written, and we have the recommendations on, and then we follow up to end it with a conference call. So we start with a conference call and end with a conference call, and throughout the whole way, we're always communicating, and we're always making sure that it's a data-driven process, which is why I think it's worth calling an Optimus process, huh? Okay, oops, still learning this. Okay, so on the load study specifically, the methodology is we start with carefully considering the weights from the drawings and or from the customer, or even from some of the process metrics that we get. Then the first methodology is always using a beam stress analysis method from engineering statics that we learned in school. And then if we need to do an alignment, misalignment consideration, we have a pretty streamlined finite element analysis for it now. Now, this is not a full-blown finite element analysis. This is a what I call, it's a lighter version because this is a not so long of a time.
So where are you getting the information that you're using to input the data? Do you have to go on site, or is that something that the customer needs to provide to us?
That's actually a really good question. We don't have to be on site because most of the weights are typically from drawings. The information that's fed from the customer, typically it's the process information. So typically if you know your tonnage, your feed rate, your production rate, and you know the speed of the unit, we can back calculate what that load would be if we were to stop that unit. So no, we don't necessarily have to be on site unless there's something else outside of the scope of the load study that we need to consider.
So if there's a customer that, say, purchased a used piece of equipment and they don't have any drawings, then how do you handle that?
So if it's that, then yes, we would either have to be on site or work with the customer on, okay, how thick is it, or get the customer to help us on some of the metrics. If it's something relatively straightforward, then we can continue as is. If it's not, then yeah, we'll have to be on site on that. Man, I like these questions. Okay, so we talked a little bit about the basics of the load study. So now what I want to do is go through, I'm trying to figure out how to go through each of the components. So for example, like I said, with weight considerations, it's a little bit different for each type of unit. So as you guys see, there's a lot of arrows, there's lots of red arrows, there's lots of black arrows, there's a whole bunch of stuff. So what you see on the left is a kiln, and what you see on the right is a dryer, or a two-pier dryer, granulator, what I would call a relatively lightweight rotary equipment. As you can see, the considerations are a little bit different. You know, you got your tire, you got your shell, all that kind of stuff. But on a kiln, you have to deal with the refractory. You have to deal with a lot more, I would say, shell thicknesses, maybe chains. And on the dryer, you have to deal more with lifters or flights on the inside, maybe some bands on the inside, and things like that. So each unit has a different set of internals, has a different set of pieces that go along with it, and just overall size. Typically on your kiln, you got a 15, 20 feet, or 10 to 20 feet to 200 to 400 feet in length. Dryers maybe 6 to 8 feet in diameter, maybe 30, 40 feet in length. So it's also just different magnitudes on the scale. Next is Hertz pressure. So I think, Sarah, you mentioned what are the metrics, right? So this is one of the first metrics. Hertz pressure, typically we like to stay under 60,000 PSI as an industry rule of thumb. This is the contact pressure between the tire and the roller. Cephas, you got anything you want to add on Hertz pressure or why it's important?
It's one of the places that you tires or materials can experience failure. I mean, Hertz pressure, because you only have, well, in theory, it's like a line contact between when it's a cylinder, right? But because they deform, it's not really a line contact, but still the area is small enough for it to have a very high stress. Okay. So that's why it's very important for us to consider that so that we don't have cracks in the tires.
Right. So high Hertz pressure, you have likelihoods of failure, or the more likelihood is it's just accelerated wear because you just got more pressure on it. If you push on something that's rolling, so let's say you got something that's rolling and you put your hand on it. If you put more pressure on it, you feel more force on it. That's kind of the idea behind this.
So does that standard apply to both kilns and dryers, or is it different?
Yes, it's normally for kilns and dryers. Where that comes from, we have still not gone that deep into it, but I like to dive even deeper into that. But yeah, in terms of some of the design metrics for our sister company OEMs that we've talked to on the dryer side, it's about 60,000 PSI, maybe 58, 55, depending on how conservative. And then on the kilns, I've seen different of the, say your major 3 or 4 OEMs, I see that number pop up often.
Yeah, I think one of the consideration is, I mean, whether it's a dryer or a kiln, you're basically using some form of steel for it. So the idea is to make sure that the pressure does not exceed the yield strength of the steel. So the 60,000 PSI is a nice round value, which depending on what steel you use, it's most of the time below the yield of it.
I like that answer better. Okay, so you got your Hertz pressure. Now we have your tire bending stress and the tire ovality. Tire bending stress is a deformation on the tire. Normal stress that the tire undergoes. Typically, again, we like to stay under 10,000 PSI. Depending on the OEM, we may or may not go with it. For example, on this graph, 10,000 PSI, we would be under. But 8,000 PSI, you may or may not be where you want to be. We tend to be a little bit more aggressive. We stick with 10, depending on how conservative. You may or may not go that route. And this is like if you've had issues with the tire before, if you had cracks before with the tire, if you're not sure the quality of the tire coming in. So again, this is where we use the metrics we use, but we work with each customer because, like people, each customer will have a certain level of risk averseness to how aggressive they are. So that's where we can work with them on the metric. Tire ovality, normal stress, normal is under a 0.2% ovality. That is normally good enough. That we've actually done some investigation in, and we're learning more and more that is quite conservative, and we're exploring possibilities on where we can change that. But that's a very standard OEM value. I think I've cross-compared 3 or 4 of them. That's a number they use pretty commonly.
So if you have a tire that's extremely worn on one pier, for example, does that increase the chance of it having a higher stress?
Yes. We did an example of, we didn't do an example. We did a study on a unit that had, and this is extreme. They had a tire thickness of 4 inches, and they've ground every year on the tire. So this is where we put the clause in that we normally don't recommend grinding all the time. So there may be some melt. So they ground that from 4 inches to 3 inches. Their tire bending stress was already about 10,000 at 4 inches. And at 3 inches, they were in the 20,000 range. So it was quite high, so high to the point I looked at the literature for their case. They're right around 20,000, and there is a limit where around that time, if one inclusion happens, they will crack the tire and fail it.
So that's an example of how the conference calls can really come in handy, because without that information from the customer about how much they'd ground, you wouldn't know otherwise, right?
Well, what happened in that one was the customer had a hard time getting capital approval. I wouldn't say capital, just having approval to take a tire that was in their in their yard, in their boneyard, where they already had a brand new tire and they couldn't get approval to get the tire installed because they didn't have this information. When they approached us, I think I told them, you need to change the tire, have a nice day, you don't need us to do a study, but they insisted, so we did the study and they got immediate approval the following day or week. So this was used as a tool to get them to get it fixed because of how severe it is. So that was really neat. Okay, so let's see, what's next? Shell stress. We have interesting things with the shell stress. So industry rule of thumb is about 3,000 psi on the stress of the shell. That's actually the mid span. So on a kiln between, let's say, the first and the tire and the second tire after that, or the uphill tire after that, it's roughly in the middle. That's where it can have 3,000 psi. It's allowed to have the most loads. What happens is the closer you are to the tire, where you have the, a thicker and thicker shell, you actually can't bend it as much. Any comments, Cephas, you want to make on the shell? I think you play with that quite a bit.
Yeah. So my thinking is that it's basically based on fatigue stress analysis. And from the studies that we've done and based on the standards that we have been using, the limits are thickness dependent. So where you have tires, you have thicker shells, whilst in the mid spans, you have thinner shells. What the standards recommend is that as the shells become thinner, the limit actually increases. And as the shells become thicker, the limit decreases. So for example, a 1 inch thickness of a shell might have maybe a limit of say 2,500 psi, whilst 3/4 might have maybe 3,000 psi. So it depends on the limit. Now, to make things easier for the designers, industry basically states 3,000 psi for the midspan. However, every unit is different. So you can go with the industry standard, or we can basically check your thicknesses and tell you the exact value for your particular unit based on standard stresses.
Yeah, I mean, I actually really like that we take a customized approach to it because each unit is a little bit different. We're not a fab shop or we're not an OEM that just kind of does wholesale everything. Each project is individual to itself, so each limit is to itself. We use an industry standard as a blanket set, but as we learn more and more, we can go tighter and tighter on certain limits. Okay, so that was shell stress. Okay, so one of the new things that we've been doing is using finite element analysis for misalignments. Okay, so these are for your 3P or more units. It gives us a little bit better resolution versus just a static beam, because a static beam, you're assuming it's a beam. Whereas finite element, you have a lot of different little calculations on it, the different nodes or the elements, and you get a little bit better resolution. We've had pretty good luck with this one. Cephas has done a lot of good work on realizing this service on top of the load study. We incorporate this as needed. We will use data that we have on any of the surveys that we do, say that like the kiln axis surveys or the DAT scans that we offer. We can use that data to model this. Now, we can also use anybody that you use for your surveys to model this too. And as you see on the right, the picture show the red, that's a high stress point on the shell. We did do one with this customer, and where that shows, we actually got confirmation there was a shell crack at that location where we predicted it would be. So this is a really neat addition to it.
So this FEA component only applies for multi-pier kilns?
Yeah, it only applies for multi-pier kilns. At the same time, as we get smarter and better, we will learn for two-pier units that there's some avenues for gaining, if it's worth gaining that resolution on it. So maybe a lighter version of, say, pads, or maybe the hood rubbing against or the shell rubbing against the hood. So there's lots of applications as we learn more and more about using a lighter version of the FEA. Now, when we do a full-blown FEA, it's a different discussion point and a different set than the load studies. Load studies are relatively quick, whereas a deeper finite element analysis is a little bit different monster, because it's even more consequential typically. With that, we have some of the results. So Cephas, you want to talk about the results a little bit on say, this example?
Yeah. So basically, this was based on data that we collected ourselves, our kiln axis survey team collected. And the image on the right, on my right, shows the displacement. It's greatly exaggerated for us to be able to see. And as you can see, where you have higher or more misalignment, you begin to see those stresses showing. Now, the issue with this is that this is a rotary system. So if it were to be static, then we may not need to bother with the stresses so much. But as it is rotating, it means those stresses go to maximum and then become, the maximum tension and then maximum compression in that area, which greatly reduces the fatigue load or the fatigue life of the shell. So that's why something like this that you can visualize and also use or get data from it is very important in misalignment studies.
So Cephas, let me see if I understand what you said. If this were not moving, if this was not rotating, you're probably okay.
Yeah.
And because you're rotating, you're cycling high tension, low tension. Say, for example, if you guys can see my mouse at this spot. So would it be a similar phenomenon as just bending a piece of copper back and forth?
Could you
copper tube, bending it back and forth?
It's similar, yes, very similar. That's basically what is happening.
You ever done that? Where you do this with a copper tube? Or a paper clip. You ever done that? With the paper clip, you do this. You do that over and over again, and what happens?
It breaks.
So you're doing this on a kiln on a I guess a much bigger, more consequential scale than a paper clip. But oh yeah, it's way dangerous on this, especially when you get hot material and it like just melts.
When you've got all the heat too.
Yeah. Man, that's great. I love that. I like the paperclip example. So with that is a load study. Okay. So a load study, you want to know the weights. The OEMs design it at a very tight design set. We've had some innovations where we add misalignment as a consideration now. As you can see with the paperclip, it's a pretty consequential one, and I think we're one of the few that really gets deep into the limits and tries to understand this entire analysis and the complexities with it.
So to consider the misalignment on a multi-pier kiln, what does the customer need to give to you? Is that, do they have to have had a survey performed in recent past?
Yes. The customer needs to show or send us a report of a survey or have one done. Because when we know that, our surveys, we have a plus or minus 1/8 of an inch limit, but as we get better and better resolution with the studies like this, we can really consider what those true limits are. What can we really play with? Excuse me. What if a customer is short on capital for the next shutdown? What can he live with? And this is kind of a practical discussion with them on, okay, we've had this, so 3/4 of an inch misalignment. Is that, we would like it to be 1/8 of an inch and everything be perfect, but we don't live in that world. So if I have that, how high of a stress is it where I can't live with it, where I can't get to the next shutdown, or, hey, you know what, can I wait a few more months and kind of go down that route? I think if we do things like that, this will really help with data how to approach the shutdowns.
So what are some indications to the customer that they need that performed?
So, if they have a heavy misalignment, right? So anytime you have a heavy misalignment, you don't, okay, and what I mean by heavy misalignment is 1/2 inch or more is what I would consider heavy. Really heavy is 1 inch or more. The issue when you have those types of misalignments is the moves you need to correct them. Sometimes the rollers are damaged. Sometimes you can't move that much because you physically don't have that space. So you need a shutdown to have those repairs or modifications in place. So then it's like, well, do I shut down to make that modification? And can we make it to that? I think those are very relevant questions, and they're high impact questions, because that's the difference between shutting down $250,000 a day, shutdown per day. You typically on a kiln, you need a couple days to shut down, a couple days to start back up, and a few days to make whatever you need to make. That's about a week. So a week is easily $500,000 to $1 million decision.
So am I correct to say if a customer has an alignment survey performed and they've got really high misalignment, then they say, okay, maybe we need to perform a load study because we're not sure if we make this adjustment, how that's going to affect.
Right, yeah.
And the load study will tell them that.
Yeah, the load study will give better resolution on that, because we now take the weight into consideration versus when we do a kiln axis survey, we try to see if the unit is straight, right? So you got a curved straw, and you're trying to make it straight or whatever. And the thing is, on a survey, it's typically a tune-up type, not a major repair. We then use other measures to see the health of the shell, et cetera, et cetera, et cetera. But if it's heavily misaligned, then it's worth doing this because, like I said, it's probably $1 million decision.
How long does one of these take?
Couple weeks, 2 weeks. Or the other thing is we can do it in 2 phases, a week to do a portion of it, a week to do another. If it's a very, very aggressive time frame, what we could do is in a week we can go ahead and discuss preliminary results, and then button everything up towards the end of the second week.
Have you ever had a customer that has performed a load study and you noticed really high stresses and recommended that they have to change certain parts or pieces of their kiln, and they've moved forward with that?
Yes, we did one in South America where we suggested a bigger tire because they were changing it was actually a cement kiln where they changed the process. So they increased it just enough that it exceeded the limits. Also, they made changes on, I think, the refractory or something else. So then it was like, okay, if 2 of your tires are one size and another tire is a different size, there's a twofold reason they wanted to take a look at that. Is one, can it take the weight change? And two, if they can, let's try to make the tires the same size so then they have redundancies in the system instead of having a 2 for 1 and 1 for 1. So they did move ahead with that.
So we've talked a lot about kilns, but on dryers, what are some examples of why a dryer user would need a load study?
So for the dryers, one example was a dryer was the 4-inch tire going down to 3 and needing to change that. That is one. Another one is with dryers, you have more likelihood of changing your speed. Dryers are notorious for speeding up and slowing down. That's a consideration, mainly the slowing down part. It's like, hey, we need to build up more bed depth. We're going to slow it down. Okay, so there's a couple things. One, a load study would be good to show the effect of the weight. But B, we've learned that you increase the torque needed on the gear just by slowing down. So that's a separate portion of it that we've learned.
But even if you are trying to increase production, so you think, I'm going to change out some flights or add some dams or something like that, you really need to consider the extra weight that you're putting on the unit.
Yes. If it's a 1-to-1, not as big of an issue. Like it's a half-inch thick flight, half-inch, okay, great. What if you went from a, you just changed the height of it? That increases the weight. So pretty much any time you change the weight, that matters. Or some of the processes and the dryers, they'll change out to a different feed. That causes changes in weight too.
And a lot of times customers are running above production limits anyway.
Yeah, these are maybe
it just makes that even more important.
Right. I mean, maybe these are designed in the 60s, 70s, and they increased it by 5% 1 year, and then you add another 5%, and by the time we have the discussion, instead of okay, so let's say you increase it 10%, should be okay. But that's a very big difference from 10% versus a 50% to 100% difference in feed rate. That's a pretty big difference, especially on a dryer, because on the kiln, the saving grace is the heavy spot is actually the refractory. And the kilns has got a little bit less production on dryer. 8 foot by 30, 8 foot by 40, 50, you could do, say on the asphalt side, I know we could do 200 tons per range, frac sand in the 200, 180, 150 tons per hour. You change that by about 50%. That's another 50 to 100 tons you just added in there. So that matters. Yeah. Other than that, we got any other final questions from you or Cephas? Hey, well, we sure appreciate it, guys. Let's, I'm glad Sarah and Cephas got to join me on this load study set. We're available. We're here. If you want to contact us, 502-515-5822. Our website is www.optimusps.com. If you want to reach us by email, info@optimusps.com. And we're on LinkedIn. We're all over social media. Have a nice day. Thank you. Thank you, guys.